Alright game, here we go. This is Chem 2, Unit 11, talking about acids and bases. In this video, we'll talk about pH and how to measure it and some simple pH practice problems here. Shouldn't be too difficult. Alright, so pH, you've probably heard it before. Not a highlighter, I'm on my pen. Alright, you've probably heard about it before. Okay, pH scale. One misconception most people have is that it goes from 1 to 14. That's not true. Okay, it can go infinitely in either direction, right? Because it's not that's not how logs work. All right. So anyway, so to find the pH of something, okay, all you have to do is take the negative log of the concentration of hydrogen. All right, or the hydrogen ion, hydronio. All right. So whenever you see this p-value in front of something, what that means is just take the negative log of it. All right, it's just shorthand for negative log. All right. Neutral pH is defined at 7. Okay. So if you have a pH at 7, you're neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. All right. Now, one interesting thing here, and this is important, okay, anything, and this is the way logarithms work. Remember that number in front of the decimal point, what that tells you is just how many spots over your decimal point is in your number. Okay, so it doesn't tell you what your measurements were, it just tells you how far over it was. All right, so it's a placeholder value. It just tells you what tenths place you're at. So the only time where you start counting significant digits for pH is after the decimal point, right? So when you're looking at your pH values, if you have a pH of 7.53, this number does not have 3 sig figs, it has 2 sig figs. All right, 2 sig figs, these two guys right there. All right, so here you've got a pH scale here on the right, okay, and they kind of show you here, and they're relating, allowing you to see the concentration of H plus and OH minus that we talked about before. And remember, if the concentration of H plus is greater than the concentration of OH minus, we're acidic. All right, so here you can kind of see that this is just 1, and then 1 times 10 to the minus 1, and then this would be 1 times 10 to the minus 14th. Don't forget our rule before that the concentration of H plus times concentration of OH minus always equals Kw, which is that 1 times 10 to the minus 14th. All right, so we have lots of other p scales, 2 of which we'll talk about for now, and then when we get to a couple videos later, we'll start talking about pKa, pKb, some other things as well. But for now, we're going to just know about these other 2 guys here. All right, so our pOH value is very, very similar to our pH. It's just the concentration, it's the negative log of the concentration of the hydroxide. All right, and then we can also have pKw, all right, which would be equal to the negative log of the Kw. All right, pretty easy. All right, now this is a pretty nifty trick using your rules from logarithms. So think back to like 6th, 7th grade or something like that when you first learned about logs. All right, and you've got hydronium times hydroxide equals our Kw, right? We established this in the last video. It has to do with the autoionization of water. And if we take the negative log of this equation, we know a rule of logs, whenever something's multiplied inside of our log, it can be split out to be added. So this would turn into the negative log of hydronium plus the negative log of hydroxide, and that would equal to our negative log of our Kw. Now the negative log of the Kw turns into 14. Right, that's the power of the log. So we're just getting rid of the times 10 value there. It just brings it down, and because of the negative side, it makes it positive. All right, that's the whole reason that negative's there. So what this really comes out to is that our pH plus our pOH is always equal to 14. And that's true at 25 degrees Celsius. All right. So let's just do some practice problems. Shouldn't be too hard. We're just going to use our new tools here. It says a solution at 25 degrees Celsius has a hydroxide ion concentration of 6.7 times 10 to the minus third. What is the pH? Well, we know from the last video that the Kw is equal to 1 times 10 to the minus 14th. And that's equal to our the concentration of our H plus times the concentration of our OH minus. All right, so that means to get the concentration of H plus, because if we want the pH, we need the concentration of H plus, because the pH is going to be equal to the negative log of the concentration of H plus. Okay, so we need the concentration of H plus there. So we can say that so our H plus concentration is equal to 1 times 10 to the minus 14th divided by our concentration of hydroxide, which is the 6.7 times 10 to the minus third. Now we should, when all said and done, we know 6.7 times 10 to the minus third is our hydroxide ion concentration, which should tell us that it's going to be basic. So we should get a pH higher than 7 when everything's all said and done if we do it all correctly. All right, so 1 times 10 to the minus 14th divided by 6.7 e to the negative third. So we got a hydrogen ion concentration of 1.1 1.49 times 10 to the minus 12th. And then we'll plug that value in here, right? So we'll take the negative log of our answer. And I got 11.826, all right? And this has 2 sig figs, so our answer should be 11.83, which is that guy right there. And it says, we got 2 practice problems here. It says, in a sample of lemon juice, H plus equals 3.8 times 10 to the minus 4th. What is the pH? All right, well, this is easy. To get the pH, we just take the negative log of the concentration of hydrogen. The concentration of hydrogen is 3.8 times 10 to the minus 4th. All right, so you just take the negative log of 3.8 e to the minus 4th. And this guy has 2 sig figs, so our answer needs 2. So remember that first one's not going to give us a sig fig, so it'd be 3.42. Well, that's not my best writing, but 3.42. All right. Commonly available window cleaning solution has a hydroxide concentration of 1.9 times 10 to the minus 6 molarity. What is the pH? All right. So this is very similar to the first one, but we're going to do it backwards. All right. Because we know that pH plus POH is equal to 14, we can use this to find our pH, because our pH would just be equal to the 14 minus the POH. All right, and so that may be 14 minus the negative log of the concentration of hydroxide, which is 1.9 times 10 to the minus 6th. So just 14 minus the negative log of 1.9 times, e to the minus 6th. All right. Boom. All right, how many sig figs here? Well, this guy has 2, so our answer needs 2, so it'd round to 8.28. All right, practice that one on your calculator if you want to do it like that, because having this negative in a negative minus a negative thing can be kind of confusing, so make sure you get that answer there. All right, let's do one more. All right. A solution formed by dissolving an antacid tablet has a pOH of 4.28. Calculate the H plus. Ooh. So this is a little different. So now for going from pH, instead of going from a concentration of H plus to pH, we're going from pH to concentration of H plus. So from before, we know that pH is going to be equal to 14 minus our pOH. All right. OH, so that means it would be 14 minus 4.82. All right, so 14 minus 4.82. All right, so I got 9.18. So that's the pH value. Now, we know that the negative log, right, of the concentration of H plus is equal to 9.18. So to get rid of that negative log, what we have to do is take the anti-log. And anti-logs are 10 to whatever the value is. Now, because we get that negative sign, we have to do this. So it would be 10 to the negative 9.18. All right. So to get the concentration of that guy, we say 10 to the negative 9.18. So we get 6. How many sig figs? This guy has 2 sig figs, so it'd just be 6.6 times 10 to the minus 10th. All right. Now we could take that value and double check it. Now let's double check it. So we'll take this value here, take the negative log of it, and that should give us our pH again. All right. Always good. And sure enough, I get that 9.8, and we could add that to 4.82, and we should get 14 again. Yep, sure enough. All right. Now, how do we measure pH? Now, pH is all fine and dandy, but it's only helpful insofar that we can actually measure that value in the lab and run with it. All right. So how do we measure that pH? Well, one way to measure the pH is actually using a pH probe or pH meter. And so here, this is kind of what they look like. They kind of look like little pens. All right. And down here at the bottom, you've got like a little glass electrode. So inside of it kind of looks something like this. All right. And so inside, like this is where the machine itself actually ends, and then you got like a little glass bulb here that's semi-permeable to electricity. All right, and so we know that the more ions that a solution has, the better off it'll be, or the more it'll conduct electricity. All right, so Essentially what this does is it sends electricity into the probe and then reads how much it gets conducted back into itself. All right, and then by measuring that change in voltage, you can calculate the pH change. Okay, and so it's not very complicated, but we'll talk about it in a future video. When we talk about electrochemistry. But anyway, like kind of how all that works, how that pH probe works. But essentially what you need to know is it sends electricity in, measures the change in voltage based on this value here. Now you have to calibrate it. There's lots of storage techniques that you have to use to keep track of these. When you're storing them for long term, you need to keep them in a buffer solution. We'll talk about what buffers mean. A buffer is essentially just a solution that's going to keep its pH at a constant rate. At a certain value and won't change very easily. All right, and then when you're done with these, you got to use distilled water. Make sure you wash off all your acid or base that you measured. All right, so on and so forth. These glass balls at the end can be pretty dang breakable. All right, so don't when you're using this, you never want to jam it at the end. That's part of the reason that it's got, like, you can see the glass bulb right here on this picture. That's the reason it's got like kind of this plastic bit here protecting it to make sure don't actually drop it against the bottom of your beaker or anything like that. All right. Another way, more simple way, you've probably seen this before, is by using indicators. Okay, we can use our indicators to help us measure pH here. I'll move my face up here so you can see that bottom picture a little better here. So they give a less accurate, right? The last one here, we can see that we get this value here, and really depending on how good your setup is, you can get 3 or 4 sig figs worth of pH data here. This one is mostly just like, well, generally, what's it look like? And so here we've got a list of different indicators that we can use to help us, and really there's hundreds of these indicators, and these are kind of some of the more common ones. You probably used phenolphthalein before, and probably bromthiamyl blue. Those are two of the most common. Methyl red's also pretty common as well. But you can see where the color change happens. So like for phenolphthalein, it's colorless when it's less than, it looks like they've got it at like 8.1, maybe 8.3, something like that. It's colorless when it's below that. And then when it's above that, it starts to turn pink, and so you get this, this color change somewhere in the middle. Bromthiamyl blue is yellow when it's less than, 6.8 or so. Kind of hard to tell on this little graph they got. And then above like 7.2, it's a dark blue. And in the middle, you kind of get this like littleish greenish yellow-blue mixture. Okay, so you can kind of use this, and they've done this nice job of setting up these beakers at different pHs. So you can see methyl red, its color changes, and so like this is your bromthiamyl blue. Here's your green that's red at 7. That's nice. And then you get your phenolphthalein, like right at 9. It's kind of like that nice pinkish color. And then at 10, it's like that dark purple. And then below that, it's colorless. And so essentially what's happening with these indicators is that they are an equilibrium mixture. And as you move from one side of the equilibrium to the other, you're just changing the structure, so it changes how it absorbs the light. So back when we talked about equilibriums, we talked about cobalt hexachloride, right? And we talked about hexachloride or hexahydrate, cobalt or something. Check the video when we talked about cobalt, and we talked about how when it's on one side versus the other, you can shift it from blue to red or purple, yellow. I don't remember anymore. But anyway, maybe this wasn't a good example to run with because now I'm not remembering all the details. But anyway, so you can use so it's the same idea. You're just moving from one side of the equilibrium to the other, and as you move from the acidic side to the basic side, you're just changing colors. And so based on where the color change happens, you can tell what pH you're at. Now, so if you've got a solution, you drop in that phenolphthalein and it turns bright pink purple, all you know for sure is it's basic. You can't quite tell what the pH is. But if you drop it in there and it's like this nice light pink, you can tell that it's 9. And so another really really common insulator is using a universal indicator, and that universal indicator has several different indicators all thrown in there together, and so so you can see like very clearly what color you are based on what pH you are, because it's got several different indicators in there affecting the color. So anyway, that's all we're going to talk about in this video. Next video, we'll talk about strong acids, strong bases, weak acid, weak bases. This stuff's going to start getting pretty hairy, so make sure you're really, really comfortable with that, the pH problems that we just did, and you can do those on your own. All right, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.